Hello everyone, my name is Haris Binzia and I'm here to present our recent work on toxicity in the decentralized web. This work is done in collaboration with researchers from Queen Mary University of London, Telefonica Research, University of Surrey, UCL and the Hong Kong University of Science and Technology. Let's start with a bit of introduction. Social networks such as Facebook and Twitter are among the most popular websites in the world right now. Despite their huge success, they are increasingly criticized for their role in disseminating harmful content such as hate speech. This is particularly problematic as their monolithic nature gives them discretion over both the definition as well as enforcement of content moderation. In reaction to this, a growing movement has emerged recently, known as Decentralized Web or DWeb for short. The goal of DWeb is to decentralize power and control away from the major centralized tech giants. The DWeb consists of a range of platforms that offer decentralized equivalents to mainstream services. Some of the popular DWeb applications include Roma and Mastodon, which are microblogging services just like Twitter. Then there is Diaspora, which is a Facebook replica for DWeb, and there are also decentralized video sharing services such as PeerTube. The DWeb platforms have several unique properties. They are made up of independently owned, operated, and moderated communities located on different servers known as instances. They enable users to sign up to a specific instance or fork up their own instance to keep control of their data. They allow users to interact locally within the instance as well as globally across instances. This involves instances interconnecting in a peer-to-peer fashion, allowing their users to communicate, which is known as federation. Any content that is being posted on these instances is known as toot, and whenever that content gets a share, this is known as reblog. The content that is being posted locally on a specific instance is known as local content, whereas the content that gets imported to a specific instance is referred to as federated content. This deep web architecture creates interesting challenges for content moderation, where centralized services such as Twitter have resources to actively moderate content by hiring moderators and refining automated classifiers using large data pools. Deep web administrators have limited resources and only control the data in their own instance. Thus, it is possible for content from poorly moderated instance to spread to other instances through peer-to-peer federation links. With this in mind, we identify four critical questions. How much toxicity exists in the D-web? How does, if at all, toxic material spread across D-web instances via federation? Can we build local classification models to reduce the amount of toxicity on instances? And lastly, can administrators cooperate to improve the content moderation on DWeb and reduce their workload? In order to answer these questions, we conduct the first large-scale study of toxicity in the decentralized web from the point of view of one of the largest decentralized microblogging services, Roma. First, we identified the list of Roma instances from the federation.info that yielded around 1360 instances. Next, we collect all public toots from the identified instances using their public timeline API. We were able to download toots from 713 instances as the rest were either down or had zero toots. We selected top 30 instances based on their toot count for our analysis. This left us with 9 million unique toots posted by 0.1 million unique users. The distribution of toots as well as users on 30 different instances is shown on your screen. In order to do the toxicity analysis, We label each toot in our dataset using the Perspective API. Perspective defines toxicity as a rude, disrespectful, or unreasonable comment that is likely to make people leave a discussion. For a given toot, Perspective returns a score between 0 and 1 for its toxicity, and we consider a toot toxic if its toxicity score is greater than 0.5. Similarly, we consider a user toxic if the average toxicity of their toots is greater than 0.5. The distribution of toxicity scores across all tools are shown in this graph. Likewise, other social media platforms, the majority of tools in our dataset are non-toxic. On average, we find the amount of toxic content is significantly less than that observed on other online fringe platforms such as 4chan and Vote. That said, we still find a large portion of toxic tools. A unique aspect of dweb is federation, whereby content is imported from one instance to another. This poses a particular challenge for local administrators who have little control over the remote instance where the content is created. To test if this concern is legitimate, we compare the percentage of local versus federated toxic tools on all 30 instances. In line with our intuition, we see that federated tools constitute the most significant chunk of the toxic content. Interestingly, this suggests that on average, users tend to follow and import content that is more toxic than the locally generated one. Now, as federated tools are more toxic, we curiously studied the reach of toxic tools. This figure shows the number of instances tools are replicated onto. In total, 50% of toxic tools are federated onto at least one other instance, and on average, toxic tools are replicated onto 3 instances versus 2 for non-toxic tools. This, however, may be misleading as different instances have different user populations. To examine the audience reach in terms of number of users, we plot the number of unique users each toot reaches. We observe that, on average, toxic tools appear on the timelines of 1.4 times as many users as the non-toxic ones. We also analyze the reblogging rate of toxic content. In order to do so, we plot the number of reblogs that toxic and non-toxic tools receive. We observe that, on average, toxic tools gain substantially more reblogs than their non-toxic counterparts. Pleroma allows its user to follow anyone in the Fediverse. By examining the followers network, we find that, on average, toxic users tend to have more followers than the non-toxic ones. Until now, we have analyzed tools regardless of their instance. However, users on different instances may hold discussions on very diverse topics with varying level of toxicity. This may play a large role in defining and identifying toxicity. Thus, we analyze the topics found in local tools using topic modeling to get a more granular view. In total, we identified 13 different topics ranging from sex to politics. Interestingly, the makeup of these conversations in terms of toxicity differs across each topic. For instance, human rights contribute just 3.7% of tools, yet constitutes one of the most significant portions of toxic content. As our dataset covers the 2019 United States presidential elections, we find extensive discussion about people such as Trump and Biden. This highly polarizing topic triggered substantial abusive language in our dataset. As topics may not be evenly distributed across all instances, we also analyze the distribution of topics on individual instances. We see that the topics discussed across instances do vary. Other than the general day-to-day discussions that occur almost everywhere, most instances prefer some topics more than the others. This flags up noticeable challenges for automating the detection of toxic content, as a single model may not generalize well across all instances. We also probe into the popularity of these topics and observe that toxic topics receive more number of reblogs than the non-toxic ones. Now, coming to the big question, can we automatically moderate toxicity on Pleroma instances? In order to find the answer to that question, we trained toxicity detection models for each instance using their respective two datasets. Our models are logistic regression classifier with bag of word features. We compare the performance of models trained on two different label schemes that are content warnings and perspective labels. Content warnings are sensitive tags that are attached to sensitive tweets by the user themselves. We observe that perspective labels perform much more better than the content warnings as they do not necessarily correspond to the typical interpretation of toxicity. Thus, we use perspective labels in lieu of actual labels as provided by the instance administrators in all our experimentation. However, this has some limitations as individual administrators may have different perceptions of toxicity or may also make mistakes during the annotation process. In order to emulate the effect of these limitations, we induce two different types of noise in our datasets. First, we flip the labels of X percentage of the truths, where X can vary from 5 to 25. Next, for each instance, we select the topic that is most popular among its users and label all its truths as non-toxic. We then repeat the training process with the noisy datasets. We observe that the topic noise decreases the average performance by only 4.7%, whereas the 25% noisy labels cause the degradation of 11.9%. In the previous experiments, we split the data in 80-20 ratio, which assumes the administrators have time to annotate 80% of the truths on their instances. This is probably infeasible due to the voluntary nature of most Roma administrators. Thus, we next evaluate how many truths each admin must label to attain reasonably good performance. For this, we generate new training sets of different sizes, ranging from 500 to 10,000, and repeat the training process. We find that, on average, an admin need more than 10k label posts to get a reasonably good classification performance. This is a significant manual effort on the administrator's end. Now the question is, how can we reduce the workload of administrators? And a potential solution lies in model sharing. To explore this, we train a model for each instance and test it on all other instances. We note that performance is very divergent across instances. Some instance models are more transferable than the others. Thus, we conclude that model sharing can work but only in particular cases. To systemize this, we propose ModPair, a system to manage model exchange between instances in the Fediverse. ModPair runs on each instance and executes three tasks. First, it automatically identifies instances suitable for model exchange based on their content. Second, it manages model exchange between the instances. And third, it employs an ensemble to merge results from the top K models predicted to be most transferable. ModPair exploits content similarity between instances to predict pairs that should exchange their models. To achieve this, each instance locally generates a vector with each component corresponding to the TF-IDF of words from the instance truths. Instances then exchange these vectors such that each instance can compute the cosine similarity between its own vector and all other vectors. This provides a measure of linguistic closeness between any two instances. By comparing the cosine similarity across instances with that of model performance, we can say that content similarity does correlate with the model performance. We next evaluate the impact of mod pair on model performance. For each instance, we apply the top three mod pair predicted models in a majority voting fashion to its truths. This allows us to calculate the newly attainable macro F1. We compare this with each instance on model and observe that consistently mod pair outperforms local training across nearly all instances. On average, Mod pair increases the macro F1 by 5.9%. We next analyze the inference performance of mod pair in scenarios where individual instance model might be noisy. We observe that even with 25% noise induced into individual models, the average performance degrades only 4.4%. By default, modpair selects the moderation models for an instance by computing the TF-ID of cosine similarity with all other instances. This may result in scalability issues as the number of instances grows. To overcome this, modpair introduces a pre-sampling strategy. More specifically, for each instance, modpair ranks all other instances by the number of followers in the target instance and then pick the top 5 instances with the most shared followers. Although this potentially misses the higher performing models, this massively reduces the number of computations. In terms of performance, we only observe a slight degradation in the average performance compared to when models are predicted from the pool of all instances. In summary, we have characterized the spread of toxicity on decentralized web, confirming that the federation process allows toxic content to spread between instances. We have further explored the challenges of moderating dweb and found that it comes with a heavy burden on instance administrators. Finally, to reduce this burden, we presented ModPair, which is a system for pairing instances that can share models. With this, we have come to the end of this presentation. Thank you so much for listening.